So, ladies and gentlemen, once again, the deadline for linear motion is Friday. If you are not happy with your unit test or your mini quiz or whatever else, please get it all done, taken care of. Get your missing and incomplete done by Friday. Okay, so today we're talking about vectors as a tool for talking about projectiles or two-dimensional motion. So the unit we're in right now is two-dimensional motion. In the previous unit in kinematics, everything moved in one dimension, either up or down or left or right, usually up or down. What we're going to find out in two-dimensional motion is that we can weave the horizontal and the vertical together and show the actual motion of objects in motion. So vectors are a tool, and the important thing about vectors is they are not scalars. Vectors have a magnitude and a direction. Your speedometer in your automobile gives you a scalar value. It gives you speed. It says you are moving 65 miles per hour. Not terribly useful unless you add that to your compass. When you add your speedometer to your compometer, you get a vector that tells you magnitude and direction. You get velocity. Okay? Distance is how far you've gone. Displacement is how far you've gone in a direction. Okay? So things that have both a magnitude and a direction are vectors. So when your play in football calls you to take the ball and run up the field would be the direction, and how fast you're moving is your magnitude. Hopefully you know to move up the field. Otherwise, you can be like Forrest Gump. You're like, you have the ball. Run. I'll run that way. No, run that way. Yeah. Totally ripped off, but here we are. Okay, any questions about vectors before we jump right in? Okay. Believe it or not, you've been using vectors for probably about 10 years now. And you just didn't realize it. Because you've been using, you remember that the first way you used to use vectors? Remember that? Back in like second grade, where you had a number line, and your number line was like, this is +5. And then this one is -3. And you added the two together and you found out what the difference was? Remember that? Oh, well, it was great times. Yeah, elementary school, you use number lines. Those are vectors. And what you were doing was vector addition. You were doing one-dimensional vector addition. So if you add this vector to that vector, in your head, you can realize that you have a vector that looks like that. Make sense? Okay. So what you're doing is called the graphical method of vector addition, where you are simply taking this vector and you are moving it parallel to itself, right up there, and you're adding that vector to that vector. The resulting vector starts here and ends here. Okay? That's called the graphical method of vector addition. Okay? It's like graphical, I'm doing it in my head. Then it's the imaginary version of vector addition. Okay? And you can assign numbers to them too. Now what if you had a vector that like this and you added one that looked like that? What's the resultant going to look like? You're going to subtract, right? Just like when you were in third grade and you had a vector that was +10 and you added to a vector that was -6, you got a vector that was +4. Remember this? Oh yeah, number lines. Yeah, Mrs. Sanders, I remember that. That was great times. Then we had nap and recess. Okay. Now if we assign numbers to them, +12 that direction and +7 or -7 that direction, we would realize that our vector result is +5. Okay. Okay, I can tell right now a lot of you are just scribbling madly because you've been trained to write down anything you see. What about this is so confusing you need to write it down? Okay, so just question. They're like some magnitude in the positive direction, some magnitude in the negative direction. You can think of like slapping the vectors onto a Cartesian plane, XY plane. So you can imagine like you slap them onto an XY plane and you have one that is +12 in the X direction and one that is -7 in the X direction. The result of the two would be something that's +5 in the positive direction.
So like, I'm just confused. Like, what is a vector vector's direction and magnitude, but like how would you use like what is it?
Oh, excellent question. How would you use them? If later on we're going to learn about forces, like if you are pushing with this much force in one direction and somebody else is pushing this much force in the other direction, the resulting force would be the difference between the two.
So like vectors, it's just a difference of the force.
Yeah. Similarly, remember the moving sidewalk exercise? You can draw the velocity vector of the moving sidewalk as +1 that way, and your velocity vector as +2 that way, so you have an overall velocity of +3. Okay? So velocity, acceleration, displacement, forces, and a whole bunch of other things we're going to learn, they are vector quantities because they have a direction. Not just a magnitude, they have a direction. Okay. So moving right along. Now two-dimensional vectors. Now we start talking about what happens if you have something moving in the x and y plane, or the north, south, and east-west plane. Now we have two-dimensional vectors. And this is where things get useful. But, this is a huge but. You have to realize motion in the x direction and the y direction are independent of each other. So, it's kind of like, if I throw this ball horizontally, I'm going to give it only horizontal motion. And because it only has horizontal motion, gravity is going to look at it and say, oh, you're moving horizontally. You continue on. I will not get act on you. Okay? But if I throw the ball horizontally, it does fall. In fact, it falls at the same rate as if I just dropped it. Because gravity doesn't really care what's going on in the horizontal direction. Gravity is going to be pulling things down in the vertical direction regardless of what they're doing in the horizontal direction. Remember that for next week when I do some fun activities and demonstrations and I ask you questions and you're like, Hollywood has told me this. Like, nope. Forget Hollywood. Forget video games. Forget Hollywood, forget video games. Motion in the x and y direction are independent of each other. Okay, so two-dimensional vectors. So we can qualitatively add vectors by drawing them head to tail. Want to see it again? Yeah, animation in PowerPoint. So you got a vector there, another vector there. You can just drag them head to tail. The resulting vector begins where the vectors begin and end where the vectors end. It's kind of like, yeah, it's kind of like if you were going to get somebody in dodgeball and you know where you're going to move. They're going to move that way, then they're going to move that way. Well, you can round it off by just throwing where they're going to end up. Like this is the resulting throw. Or if you're driving somewhere, it's like, I need to go to my mom's house and then I need to go to my best friend's house. And you're like, or I can take a helicopter and just go right there.
You can just drive over people.
Yeah, if you have a Jeep, you can just drive over houses and stuff. Okay, here's another vector and another vector. Draw them head to tail, and that's where the vector starts, that's where the vector ends. Now, vector addition is commutative. What do I mean by that? Exactly. The way or the order doesn't matter. Doesn't matter if I add this vector up here, or this vector here. Doesn't matter what order I add them, as long as I am head to tail, the resulting vector is going to be the same way. Now here's another thing about vectors. It doesn't matter where you put them. All vectors care about is their magnitude and direction. So I could put a vector right here, and another vector right here, and another vector right here. These three vectors are all this vector. They've just been moved somewhere on the plane. That moving somewhere on the plane is called translation. They've been translated about the plane. Okay. But they all have the same magnitude. They all have the same direction, except for this one, because it's kind of tricky. But they have the same magnitude. They have the same direction. So they are the same vector. Make sense? Okay. Give me a thumbs up if you're ready to do your own. Okay, so scribble these guys down. Draw the resultant vectors of these. And after you've done draw the resultant vector, compare it with your neighbor. I'm sorry, back row. Again, you are welcome to pull your chair up and move up even if you don't want to stay up here permanently. You can drag your chairs up to the front. I feel like I should yodel at you back here. So once you've added them, again, add them head to tail. And then draw a resultant vector that starts where the vectors start and end where the vectors end. Once you've done that, show your neighbor and see who is the best artist among you. Pain in the butt. It really is. That's partially it, yeah. And then beard dandruff. You're like, oh crap, it's all over me. Yeah. And you eat and like food particle gets in there. Just,
I trimmed this for homecoming. It's hard.
yeah. Okay, with a show of hands, like what direction it goes, show me what your resultant vector looks like. Okay, I'm seeing lots of vectors that look like that. All right, let's see if my diagram agrees with you. So I took that vector, I added to that vector, and I got a vector that looks kind of like that. Yeah. Yeah, it'll totally work. It doesn't matter which vector you start with and which vector you end with. You will have a vector that's going to end up looking like that. Okay. Questions? Sylvie? I got to get you a megaphone. Okay, say again. Yes. The resulting vector starts where the vectors start and end where the vectors end. So you have a chain of vectors. The resulting one will start at the back of the first vector and end at the nose of the last vector. Okay, here's one more. Okay, once again, show your result to your neighbor, and then rub it in their face if you're a better artist than they are. Okay, show me with your hand. Where does the resultant vector point? Okay. I'm seeing some upward directions. I'm seeing some horizontal directions. Hopefully your vector, if you drew it head to tail, you had a mostly vertical-ish vector. Yeah. Let me give you the pitfall. The pitfall in doing graphical vector addition is this. The exercise will be like, okay, I got a vector there and a vector there. And you're like, oh, they already connected them. I'll just connect them like that. Don't do that. Okay? Don't let them fool you. So if they give you a vector like that, make sure your next vector is like this, and that's the resulting vector. Okay? Again, vectors must be head to tail. Question? Yep. All right. You don't need to write anything down here, but it's kind of fun. So it doesn't matter how many vectors we have. You can add 2 vectors, 3 vectors, 4 vectors, 18 vectors, or 450 vectors. It doesn't matter how many vectors you have. The resulting vectors, or the resultant vector will still be the same. See if you can, in your mind's eye, figure out the resulting vector of this. I'm going to add that vector. I'm going to arbitrarily choose to add that vector next, then that vector, and there's the resulting vector. Looks like that. Questions? And I'm not going to bring this up, but if you ever want to like just play with vectors, there's a simulation in the PhET that we're going to be playing with on Friday. Okay, Friday. And if you just search for a vector calculator, there are lots of vector calculators. I think it might be like one of those things you have to program when you're learning how to program. Okay, next. Oh, so you were writing stuff down? Oh, okay.
I'm sorry, I have to pass this. Okay, we got it.
It's also going to be up on the YouTubes. On the YouTubes. Yeah, so you can always review it on the YouTubes. All right, now, you got a question before we move on.
Yeah. Are the arrows supposed to like meet like another example? Okay.
I'm limited by what I can drag in PowerPoint, but yes, they should always go head to tail, head to tail, head to tail, and then from where you start to where you end.
So the end is like head to head.
Yeah, you can basically like from this point, which is end, to this point, which is start. So,
Okay.
yeah. Okay, now when we break vectors into their components, when we take a diagonal vector or a non-horizontal or non-vertical vector, when we break it into its components, we call that resolution. So we resolve something into its components. Okay. This is like, again, you're going to run a route where your coach tells you go up 10 yards and then over 5 yards, and the quarterback is going to throw the ball to where you should be. Okay. So sometimes you run like that, and you're like, well, why don't I just run this way? You're like, no, you have to confuse them. Okay. So you're going to resolve your vector into its components. So here we have a nice fun vector with a 45-degree angle, and it has x and y components. So when you're looking at vectors, imagine or draw a Cartesian plane on top of the vector with the base of the vector right at the origin. The angle of the vector, theta, this is Greek letter theta. You've probably seen it in your math classes. It's a circle with a line through it.
Yeah.
Okay, so it means angle. Yeah. Anyway, so when you resolve your vector into its components, you look at the magnitude. This is the magnitude. The length, the bigness is the magnitude. And then the angle to the 0, basically the angle to the horizontal axis. I love this animation. I wish it came out better, but it's totally cool. So the magnitude has vector m, and then to find the x, we use the cosine, because this is the x right here. You can imagine it's making a triangle. It's making a right triangle. So, quick review of trigonometry. What is cosine? Cool. Opposite over adjective. I mean adjacent. Okay. Hypotenuse. Opposite over hypotenuse. Adjacent over hypotenuse. Adjective over hypotenuse?
Yeah, that's correct.
We like this one better? Okay. And what is sine? Opposite over hypotenuse? We're all agreed that it's that opposite over hypotenuse? Okay. Adjacent over hypotenuse, opposite over hypotenuse. And if you want to use the tangent, what would be tangent? Opposite over the adjective? I mean adjacent? Okay. I object. Okay. So quick review of trigonometry. If you're not there yet, then lean over to your neighbor and have them teach you SOHCAHTOA, or come in after school and we'll talk all about how to make triangles. Because these are really the only trig functions we're going to use in physics. I realize people tell you, physics is hard, you need calculus. You don't. You just need cosine, sine, and tangent, and then you're done. Okay, so since we're looking at this leg, we're breaking this vector into its components into a y leg and an x leg. So our x leg is the adjacent leg, and the magnitude is going to be our hypotenuse. So the x value is just going to be the cosine, which is the over the theta times magnitude. I don't get it, Mr. Byers. Prove it to me. Okay. So the cosine of the angle, which is that, is adjacent over hypotenuse, right?
Yes.
Okay. So adjacent would be the x value, and hypotenuse would be the magnitude. Can you see this in the back row? Okay. Should hand out magnifying or telescopes. Okay, so the cosine of this angle is the adjacent leg, which is the x value, over the hypotenuse, which is the m value. So if we want to solve for x, we're going to multiply both sides by m. And we get this. X equals cosine theta m. Make sense? All right. And we can do the same thing with sine. So the sine of the angle is the opposite leg, which is the y leg right here. Here's our y leg over our hypotenuse. So if you want to know what the y leg is, we're going to multiply both sides, and we're going to get sine theta m. Did your math teacher ever tell you what sine means, or where the word came from?
No. Not really.
You're just using the same word over and over again? Sine comes from the word sinister.
What's 666? Has something to do with 6.
I gotta show you something.
Yeah. Yes. Yes.
It's not all that exciting, but I haven't actually done this before, but I'm wondering if I can just find an optical prescription. You've all actually seen this, you just didn't realize it.
Red eyeglasses.
Yeah. Let's see if anybody has uploaded their prescription as an image. How to read your prescription. Okay. The first step to understanding your eyeglass prescription is knowing that OD means oculus dexter, which literally means hand-eye or eye-hand. And oculus sinister, which literally means eye opposite. Sinister means opposite. And the story goes like this. And whether it's right or wrong, I think it's a great story, so I'm just going to tell it to you, because someone told me when I was younger. The way it worked was when the Greeks were coming up with a word to mean opposite, they used sinister, which means away or opposite. Because when you struck a deal, you used your right hand. And people who were left-handed weren't trusted. And to make sure their little groups stayed little groups, certain individuals, and I'm going to say who, in case there are people who are related to them, used their left hand for all their deals, so they wouldn't be thought of as the Greeks. Yeah, so the Greeks shook hand with their right hand and made deals with the right hand, and their other group used their left hand. So those other groups, which the Greeks didn't really like, were called sinister or opposite.
Boy Scouts of America.
No.
Left-hand shape.
Really?
Yeah.
Oh, there you go. So the Boy Scouts are following that pattern too. Anyway, but yeah, so sinister means opposite. So if you're left-handed, sorry, you're sinister.
Cool.
Yeah.
That explains
You can go tell your parents and like, I'm left-handed, so I'm sinister. Yeah. And sine means opposite. So sine, so there you go. So never forget that sine means opposite, sinister. I think that's kind of fun. Yeah. Okay, so now we're going to use the tools that we have to break these vectors into their components. And this is going to require a calculator. Please make sure your calculator is in DEGs. Okay. This is the hardest part about two-dimensional motion, is remembering to put your calculator in DEGs. If it's in rads, if you have a rad calculator, that's not going to work until you get into rotational motion in December. Okay, so we'll do the first one together just so we're all on the same pattern. Number 1 has a magnitude of 10 units and an angle of 15 degrees. So to find the x value, or the x component, we're going to take 10 cosine 15. And to find the y component of number 1, we're going to take 10 sine 15. So bang those into your calculator, and then imagine this as sitting on the middle of a Cartesian plane. See if your x and y values look reasonable to you. Here's your y value, here's your x value. And please write these down, because we're not going to get through everything today. We're going to have to finish the PowerPoint tomorrow. And I don't want to have to do all of this all over again. So write down the values you get. Even if you're one of those people like, I don't take notes, I just watch. Is that the yellow one? Let's take a look.
I feel like I could get onto the internet and watch cat videos with it.
You can't, but that's the trig button. So just trig. So 10 cosine.
But it's in radian.
Oh, good call. How do I turn you into rad? How do I? Let's just keep taking out another one until we find that's in degrees. Shoot. Here, use this in the meantime.
Oh my. No, we're just using TI-30 techniques.
Yeah, if you have one of the yellow ones, I don't know how to put it in degrees yet. You grab one of the blue ones. It's not going to be the same answer. Because it actually says rad up top. Okay, fine. So go pi over 12. Pi over 12 is 15 degrees, so pi over 12. Well, okay. Nolan is going to figure it out. Yeah. I need to write down like how to use the yellow calculators.
Stop touching me like that.
It's basically saying like, see like, who's a really good person because it always really stuff.
Oh well, I don't have the patience to work on it right now. Okay, so someone who does have a normal calculator, what do you have a value for a value of x?
9.7.
9.7? Sounds great. And a value for y?
2.6.
2.6. Okay, so based on the graph, does y look like it could be 2.6? And does x look like it could be 9.7? Sounds good to me. Okay, so break the remainder into their x and y components and write them down. The pattern works the same way. Yes, do the rest of them. I figured it out. If you have the yellow one, you go to the menu, and then you go to Document Settings until you see the Document Settings, and then you go down to Angle, and you choose Radians. And you select Degrees. Then you say Make Default. Hey, cool. Okay, now this one's in default degs. Is there anyone who needs help getting started? You're like, I've completely gone off the rails. Okay.
I typed the thing and it's just not showing up.
You're doing the graph? All you're going to get is, we don't care about the graph. We want the actual magnitude.
Oh, you want that?
Yeah.
Okay.
So you know what I'm going to do? Is I'm going to go to the menu. Escape, escape.
I changed it to degrees.
You... Not in the calculation, but I'm about to. All right.
So,
Yeah.
when we get a negative number, is there such thing as negative?
Absolutely. It just means it's pointing into quadrant 3.
Who told you Y was 2.6?
You guys did. 2.4?
We got 2.6. It shows a fraction and a 1, and then it also kisses the 2.58.
Oh, you resolved them. I don't know what you're doing there. You're all up in the tangents and.
Oh.
We're just doing the components. We're not actually adding anything just yet. Okay, do you have an x component for number 2 for me?
1.04.
1.0? Okay. And do you have a y component for me? 5.9. And for component vector 3, do you have an x component for me? Negative 4.7. And a y component? Negative 1.7. Okay. So do those values look like they could match these? All right. Now, we've pretty much mastered graphical vector addition. Now let's actually find out exactly what they are. Let's add vector 1 to vector 2. Okay, watch this. This is how we do this. Elias, do you have a question before we move on? Okay, this is how we actually add our vectors. We add the x value of 1 to the x value of 2. We add the y value of 1 to the y value of 2. And what we're going to get is a resulting x and a resulting y. So we're going to add 1x plus 2x, and that's going to give us the resulting x. We're going to add 1y to 2y, and that's going to give us a resulting y. The angle will be found with the inverse tangent of resulting y over resulting x. That's going to be the angle. And the magnitude of the resulting will be Pythagorean. The resulting y, quantity squared, plus the resulting x, quantity squared, that quantity under the radical. So let's walk through the steps with the remaining few minutes we have, and we'll see how much we can get done today. Okay, 1x plus 2x is going to be 9.7 plus 1.0, which is going to be 10.7. And then 1y is 2.6 plus 5.9, and that's going to equal 8.5. So if I added this vector to that vector, it's going to give me a vector, it's going to look kind of like that. That's going to be our resultant. That gigantic vector is our resultant. Does it look like that gigantic vector is 10x and 8y? Okay. So the last step we would do is we'd put in the inverse tangent of, ry, which is 8.5, over rx, which is 10.7. That's going to give me the angle. And my magnitude is going to be the radical of 8.5 squared plus 10.7 squared. So we have about a minute left. You can bang on your calculator if you want, but we'll pick up this activity tomorrow. Any questions before you depart?
No.
Okay, so Nolan's the spokesperson. Nolan says we have no questions. Okay.